All right, class, so next we're going to talk about how to find the domain of functions. One thing that I find incredibly helpful is to try and visualize what each of these functions looks like, and to keep in mind that you can never divide by 0. So let's take a look at problem 1. The graph of problem 1 is a line, right? It has negative slope, so it looks like it's going downhill. And we know that all lines of the form y equals mx plus b have a domain from negative infinity to positive infinity. The same is also true for quadratics. So for instance, if I had a quadratic, its graph would look like a parabola, and its domain would also be from negative infinity to positive infinity. What changes is its range. Next, I have for problem 2, I have 1 over x. This is called the reciprocal function. It's also an example of a rational function. That's where I have a function divided by another function. So remember, the domain is going to be all possible x values that this graph or function could take on. But there's one function, one x value that this function can't take on, and that's when x is 0, right? If I had x equals 0, I'd be dividing by 0, which would be bad, right? That'd be undefined. So the domain for this is, I could write it in interval notation, or I could write it in set notation, and that would be x such that, that's what this bar means, such that x doesn't equal 0. So this says all x as long as x doesn't equal 0. This next example, number 3, 4x plus 5, that's an example of a linear equation. This time we have positive slope, so my graph will look like it's going uphill, and its domain is also from negative infinity to positive infinity. Now for examples 4 and 5, I want us to keep in mind that these are indeed rational functions. So what can my denominator never equal when I'm working with rational functions? Well, our denominator could never equal 0, because then we would have to divide by 0. So in order to determine which values of x would make our denominator equal to 0, we could set it equal to 0 and solve. So I would add 3 to both sides. That gives me 2x equals 3. I divide by 2, so I get x equals 3 halves. That means that my domain for problem 4, it's going to go from negative infinity to 3 halves, and then we close our parentheses, meaning 3 halves is not included. We jump over that point and go from 3 halves to positive infinity. This could also be written in interval notation, x such that x doesn't equal 3 halves. So that was for problem 4. Let's do problem 5 in orange, and then we'll probably have to make ourselves some more room. So for problem 5, I have 16 minus x squared. So I'm going to go ahead and set that denominator equal to 0. I'm going to subtract 16 from both sides. Negative x squared equals negative 16. Divide by negative 1. X squared equals 16. I take the square root of both sides. I get x equals plus or minus 4. Right? If I take the square root, positive number, my result's going to have a plus or minus 4. So that means that the two values that are being left out of my domain are when x is negative 4 and when x is positive 4. So I can write my domain as an interval from negative 4 to 4, and then we're going to union that from 4 to infinity. I could also write it in interval notation, x such that x doesn't equal negative 4 or 4. Whether you write your domain in interval notation or set builder notation, I do not care. Typically, on an exam, I may ask you to do both, but they are both equivalent. So before we jump into our radical functions, why don't we make ourselves a little bit more room? So next I have f of x equals the square root of x. Now remember, I can only take the square root of positive numbers, okay? What's the smallest number I can take the square root of? 0. So our domain is going to go from 0, with 0 included, all the way to positive infinity. The graph of this rational function looks like this. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is the square root of 2. 4y is 2, right? Square root of 4 is 2. So it's going to look like this. Next, if I have, for problem 7, f of x equals the square root of negative 3, I know the smallest number I can take a square root of is 0. So I need to figure out what value would make this denominator a 0 by setting what's under my radical equal to 0. I add 3 to both sides, I get x equals 3. This tells me where my graph is going to start. If I have x is 3, that's the square root of 3 minus 3, which is 0. If I have x is 4, that's the square root of 4 minus 3, which is square root of 1, which is 1. Right? So kind of what this did, and we're going to talk about this more as we go on in this text, in this chapter actually, is it shifted my graph to the right 3. So my domain for my green graph goes from 3, with 3 included, all the way to positive infinity. Last but not least, let's take a look at problem 8. So I have f of x equals the cube root of negative x. The cube root of negative x, this graph kind of looks like this, right? Why? Because if I have negative numbers, that's what's over here, the negative numbers, I can take the square root of negative numbers, right? The cube root of negative numbers. The cube root of negative 8 is negative 2. Cube root of negative 27 is negative 3. So because I can take the cube root of any negative number, and I can also take the cube root of any positive number, my domain is going to be all real numbers. So you can write it like this. You could also write R. You can write all real numbers. They all mean the same thing. It just lets me know that you know what the domain of these functions are.